Hello and welcome to this video. My name is Colin Greatwood and I'm a part of the Mechatronics Technology Engineering team here at Festo. Today we'll be walking through how to set up a MURR remote I/O block to control a simplified motion series actuator from Festo. You can see I have a blank project here open and my components are in the bottom left corner. I have a 24-volt power supply, a Siemens 1200 series PLC, a 5-port netgear switch, unmanaged, a MURR standard remote I/O block. You'll see I have one device connected to one of its ports, and that is a Festo EPCE small rod style actuator in the bottom left. Now the first thing I'll do is add some devices to my project. Double click on Devices and Network, and then add a new device. I'll search for the CPU I'm using here today, which is a 1212. A 1212 FC DC-DC relay. Click that and check the right version. Today I'll be using version 4.4. Once it's added to the project, I'll go to the general properties for that PLC in the device view and double check the IP address on the right subnet. Here you can see the IPv4 is set to 192.168.0.1 with subnet mask 255.255.255.0. The PROFINET device name is set automatically. Next, I'll add my MURR remote I/O block. It's a standard version. Under Other Field Devices, PROFINET I/O, MURR Electronic, and here notice I don't pick the Pro MPN I/O, I pick the standard. The part we're using today is 55532. That article number can be found on the body of the physical device. I'll network this remote I/O block with the PLC by clicking and dragging the green network square to that of the PLC1. You'll see this creates PROFINET network PLC1 and that my remote I/O block gets assigned to PLC1. Double click to enter the device view of that remote I/O block. Under the general properties, you'll see here that the IP address is the next available, 192.168.0.2 with the same subnet mask as that of the PLC. And the PROFINET device name is auto-assigned for this device as well. You can see in the top of the device view, there are some slots available for assigning devices. As mentioned earlier, there are 4 ports on the left and 4 ports on the right of this standard block. The 4 on the right are the IO-Link ports, and the 4 on the left are the digital I/O only ports. I have one device here on the right-hand side for IO-Link. So I won't add anything to the digital I/O ports here at slot 1.1 through 1.5. On the right-hand side, slot 2, you see I have IO-Link ports 1, 2, 3, and 4. However, the physical labeling on the standard block here is X4, 5, 6, and 7. So X4 will be IO-Link port 1. I'll add my device here. Under the hardware catalog, go to Submodules, Device, IO-Link Input and Output. Now the simplified motion series actuator needs 3 bytes in and 2 bytes out. The closest configuration for this MURR block, which is pulled from the GSDML file, is IOL-IO 4 bytes in and 2 bytes out. We'll need the 2 bytes out exactly. The 4 bytes in is just due to byte boundaries. It will not cause any problems. Click and drag that to IO-Link port 1, which again corresponds with connector X4. For the other 3 ports, 2, 3, and 4, go into the IO-Link SIO mode, find deactivated, and assign those 3 ports to be deactivated by default. Next, we'll need to go and download some software to make the SMS actuator work. Go to Festo.com. Within Festo.com, search for the specific part number of that actuator. You can find this on the side body of the actuator. You can see here we're working with 8102168. When I go to that device landing page, I'll go to the download section, expert knowledge, and then look for the application note, simplified motion series control with Siemens through CPX API. This will give me a walkthrough of how to set up the device. Download and extract that application note. Once it's extracted, open that folder. Within it, there are 3 subfolders for App Note, Library, and the Sample Project. The application note will give you a walkthrough of most of what we've already done. The sample project will also be very similar to what we've set up already. We will need to access the library in subfolder 2. Copy that folder, go back to your project, and click on Libraries on the right-hand side of TIA Portal. At the bottom of this side panel, you'll see Global Libraries. Click Open Global Library and search for the folder you just extracted to, subfolder 2, Library. Within these, you'll find a .al14 file. That is a global library created for TIA Portal 14. You may have to upgrade this if you haven't done so already. Once the library has been upgraded, you'll then see it added to your global libraries list as V17. Drilling down into that library, you'll see there are 5 different main function blocks: SMS Festo Advanced, Basic, Intermediate, I/O, and Parameter. Today I'll be using the SMS Festo Advanced block. Click and drag that to Network 1 of main OB1. It will bring in all the supporting functions and system blocks needed. The first thing you'll have to add is the ref inputs and outputs. Go back to the device view for the MURR I/O block and select the channel for your SMS device, IO-Link port 1. Notice that your input and output addressing starts at byte 68 to 71 and 64 to 65. You'll need the second byte of each of those assemblies here. So for the inputs, use %IB69, which was the second byte in the inputs assembly. For the ref outputs tag, you'll also need that as well, the second byte in the output assembly, %QB65. Lastly, for by device available, you'll need the third byte in the input assembly, %IB70. Then address all the other tags as you see fit or from the assigned data block 2. I'll do that quickly. Next, I'll create a watch table so that I can step through some of the functions associated with the SMS actuator. Here I've created a watch table for an SMS test sequence where you can see I established communication all the way through motion. To test this, I'll compile, download, and go online with the actuator. Making sure that my CPU is in run mode, I'll come back to my watch table to test some functions. For the process and parameter channel data, or cyclic and acyclic you'll need to set up the communication parameters at the top of this watch table first. Hardware ID, ICAP, and iPort. First, for the hardware ID. The hardware ID for a standard block depends on if you're using a standard or pro. As I've mentioned several times, we're using a standard MURR block today. Therefore, for the hardware ID, we'll need the IOLD or IO-Link device proxy for this specific channel that we're controlling. So I'll go back to the device view of the MURR block, click on IO-Link port 1 for the SMS device, go to the properties for that channel, and then click System Constants. Here you'll see the hardware identifier 280 for that specific channel. It's important that you use the IOLD proxy and not the IOLM for a standard block. So you see I have 280 listed here. Next, you'll need the ICAP. This is a number assigned from PI for all products and manufacturers using IO-Link. There are 3 assigned to MURR Electronic. Depending on how old the product you're using is, you may have 3 different values that you need to use here. The first is 255, second is 227, and the third is 46080. By trial and error, I've eliminated the other 2 and know that 255 is correct for this specific model. Lastly, you'll need the iPort. This is a 1-based index dependent on which IO-Link port you're connected to. From the device view, you know that this was IO-Link port 1. Now I'll rearrange my windows so you can see me testing things a little more clearly using both the function block and the watch table. Now I've established my communication parameters, and using the little lightning bolt, I have forced those over to the function block. You can see on the right-hand side that they're already there. Next, I'll enable the function block using xenable. This allows for process and parameter channel data to be passed through it. I verify it's enabled with xenabled, and then I apply power to the load side of the SMS stepper drive. Next, I'll preload some speed, force, and position data. This is processed over the acyclic parameter channel. I will have to explicitly force this to the function block. I do know that this actuator has a 30 millimeter stroke limit, so you can see I've loaded that here. Lastly, I'll toggle the xstore parameters input on to true and then off to false. It's important you return this to false. Now my parameters are stored. My device is ready as seen by xstate device. If I wasn't getting this, or if I was getting both xstate in and out simultaneously, I may need to execute reference. So I'll do that here, although I'm already referenced, and you can see my actuator is moving through its full stroke. Now you can see I'm getting both xstate devices true and state out, since I'm extended. Using the process data, which is again cyclically processed, I'll test that that is working correctly by using xMoveIn and xMoveOut. Since I'm already out, I'll toggle xMoveIn from false to true. My actuator moved, turn that false, and now I'll use xMoveOut to move it true, and you see I extend. So now I've verified that my process data is working correctly. Next, I'll change my speed out from 10% to 100% and do the same for speed in. I'll preload those to the function block and then test that my speed has been increased using the process data. Toggle xMoveIn to true, and then xMoveOut, you see I'm moving much faster. Now I've verified that my parameter data is working. Thank you for watching.